Welcome to my thesis presentation about electrical propulsion systems for civil transportation aircraft. We will focus in this talk on a new full electric drivetrain configuration for large aircraft and related studies to assess the potentials and limitations of this concept. Aviation faces a demanding emission reduction goal required by international authorities, and the pollutants in focus are carbon dioxide, nitrogen oxides, and noise. Thereby, there's a growing interest in electrical propulsion schemes in the aviation community. Recent electrical drivetrains apply mostly an engine-oriented drivetrain design with centralized power generation to serve the engine design and a decentralized thrust generation, which serves aircraft design. This is called an turboelectric propulsion system, and if we add some auxiliary power supplies like batteries or fuel cells, we get an hybrid electric drivetrain with also centralized power supplies, auxiliary power supplies, which are intended to serve engine operation. This is then connected by a power distribution grid, which has added mass and complexity. And all this could be implemented like this. In this picture, we see an aircraft with distributed electrical propulsion systems and then centralized power generation on top of the fuselage. If you now take out the turboshaft engines, you get a full electric drivetrain, as it is common in literature. But actually, the power centralization shown here is unnecessary for full electric drivetrains. Instead, we are proposing an electronics-oriented drivetrain design with a decentralized power generation, which serves electronics design, and then decentralized thrust generation, which serves aircraft design. By this, we get an autonomous, separate entity, which can actually refer to as electrical engine. Before we dive deeper into this concept, we will first examine the external constraints which this electrical engine faces in aviation applications. We will determine the energy source and then address the engine concept with its engine components and the construction. By this, we obtain holistic electrical engine model, which is ready to retrofit to some aircraft to determine limitations and potentials. We close the presentation with a conclusion and an outlook on future work. Regarding the external constraints, first of all, we need to comply with the CS25 certification specification. The other main aspect is that we should consider the environmental conditions as temperature and pressure will drop with increasing altitude. This can be modeled according to the international standard atmosphere, and we expanded this by a heat capacity calculation based on findings of Mr. Lemon et al. And we also adopted the A350 extreme weather test conditions to reflect the airfield conditions which are not covered in the international standard atmosphere. Further, we should also have a look at the cosmic radiation, as the cosmic radiation will significantly increase, as you can see here on the right-hand side, with an altitude of 6 kilometers. This would be the radiation at highest terrestrial applications, which is about 0.5 microsievert per hour. But at common cruise flights, we will face a radiation dose which is 18-fold higher. So we should have an eye on that. Let's go on with the energy source. We will apply hydrogen as the most efficient sustainable fuel, as hydrogen itself is feedstock to synthetic fuels and therefore has a lower power energy demand for production. Further, we will apply that in liquefied form, since liquefied hydrogen has the highest volumetric energy density among the storage options of hydrogen, and comes along with a very low temperature of minus 253 degrees C, which supports the cooling system design later on. Regarding the electrical concept, we actually electrify a conventional engine. We will change the engine core to a turbocharger and add an electrical drivetrain and a cooling system. By this, we get an integrated autonomous electrical thrust source, and we can enjoy the advantage that we do not need a high power transmission. We are still compatible with distributed propulsion and with the CS25 specification. Further, we are operating on comparably low temperatures with regard to conventional engines and can therefore facilitate lightweight design. The concept itself comes along with two variants. First, we have the direct drive engine, which connects the electrical motor directly with the propulsor. The engine itself splits into several engine modules, whereas each module has a cooling system, propulsion module, so propulsor is segmented low-speed electrical machine, and a turbocharger. The turbocharger has a task to stabilize the fuel cell temperature and pressure and to recuperate some energy from the exhaust gas. The other variant is the gear drive engine, which actually puts a gearbox between the electrical machines and the propulsor. Thereby, we are connecting the propulsor individually to each gearbox to avoid single point of failures due to a blocking gearbox in the system. Regarding the propulsion modules, we can see here a propulsion module of a direct drive engine, which has on the right-hand side a fuel cell, a share in the turbocharger drive, and the supply for a single segment of the electrical motor. In this concept, the electrical machine will combine all individual propulsion module powers to the entire engine module power. For the gear drive engine, the propulsion module looks actually much the same, but we have an individual electrical motor. And the combination of the individual propulsion module powers is then done by the gearbox, which hands it on to the propulsor. Regarding the engine components, we had a look in our thesis on electrical machines, power electronics, power source, protection systems, and the cooling system. Let's start with electrical machines. For the direct drive engine, we will need a low-speed electrical machine with highest power density. The most suitable machine type in this case is a fully superconductive electrical machine. And for this, we adopt the machine concept of Mr. Balachandran et al. From the University of Illinois. The machine is shown here. And the authors provide a machine, which is actually a synchronous machine with a rotating armature and a stationary field winding. It is supplied via slip rings and has a slim iron shield, but no stator or iron, rotor iron. This is the most power-dense motor which we found in literature, and the author claimed that they can reach with this motor an efficiency of 99.9%, a power density of 50 kilowatt per kilogram at an operation temperature of minus 253 degrees C. We further assume that this efficiency is load independent. Further, that the power density is independent of the power rating and the segmentation which applies for the direct drive engine. Further, we assume that we can apply direct liquid hydrogen cooling. And by this, we obtain a best case scenario to benchmark the gear drive engines later on. The gear drive engines will require a high-speed electrical machine. Since for a given mechanical power, we can reduce the iron and conductor mass by reducing the torque and hence increasing the speed. For this, the switch electric machine is best suited as it has mechanical advantages, since the set has only bare iron on its rotor. And therefore suitable for highest mechanical loads. Unfortunately, we faced a fully constrained design space, so we developed a new analytical SRM design tool, which can computate a single switch electric machine in 23 milliseconds on a conventional laptop. And by this, we were capable to investigate millions of switch electric machine configuration, and we found the following model. Our switch electric machine needs to be in pancake shape due to limitations by bending resonance. Further, we need a very strong rotor lamination to withstand the high centrifugal load. And we will apply a direct cooling scheme to decouple the heat rejection from magnetic flux conduction. Further, we will apply the lowest phase voltage without impact on power density, which is in our case 1 kilowatt. And we will select the efficiency and winding temperature rather to facilitate preheated design. And in our case, we will choose 95% efficiency and 27 degrees C operation temperature. We will apply a 250 kilowatt SRM with a speed, with a mechanical speed of 87,000 RPM, the power density of 20.3 kilowatt per kilogram, and a 500 kilowatt switch electric machine with a mechanical speed of 62,000 rounds per minute, and a power density of 16.3 kilowatt per kilogram. Since we are not only interested in weighted operation, which corresponds to operation during takeoff, but also in partial load operations as during top of climb, and especially during cruise, which is the flight status, which governs the fuel burn of the aircraft, we need some information about the partial load behavior of the switch lattice machine. The design tool can only provide rated efficiency. So we combined the measurements of the switch lattice machine OCOFE version 3 from the dissertation of Mr. Carstensen with the propulsion power requirements of an A320-200, which has been provided by the Institute for Aerospace Systems. We can see here that at takeoff, we will operate at rated efficiency, doing top of climb, which is marked here with TOC. We are operating at an efficiency 0.5% below rated efficiency, and during cruise, we will operate on an efficiency 1.5% below rated efficiency. Further, we need a gearbox. Power combining gearboxes are state of the art, applied in helicopters, wind turbines, or turboprop engines, for example. And we will apply the gearbox model of Mr. Stuckel, who provided a model for weight and efficiency estimation of gearboxes. And we can see on the lower right-hand side that the main driver and weight for the gearbox is the speed of the output spool. We can see that the lower graphs are related to a propulsor speed of 1,200 RPM, whereas the higher power density relates to an output speed of 3,500 rounds per minute. We can also see that the input speed is of rather minor importance, as it is given on the x-axis and has a low effect on the power density itself. The model of Mr. Stuckel doesn't provide any information about the size of the gearbox, so we will apply the volumetric power density of the gearbox of the T56 turboprop engine, which is 2.5 kilowatt per liters. Let's go on with the power electronics. In principle, we face two main issues: low ambient pressure and intensive radiation. So we should head on for low operation voltages to reduce our isolation demands. And we should apply high operation temperatures to enable the formation of avalanches within the power semiconductors. Further, we should head for low complexity to reduce the number of sensible components. And we should keep in mind that the actual failure result of an power electronic converter failing is limited ultimately by the modular drivetrain design. So the loss in propulsion power can be mitigated. We will apply in this case the silicon carbide power semiconductors, since they are compatible with high temperature operation, lead to a low device count, and have low losses. The power density of the power electronics will be estimated based on the findings of Mr. Wienhausen, who demonstrated the power density of a buck boost converter of 53.6 kilowatt per kilogram and a volumetric power density of 98.1 kilowatt per liters. The basic schematic of the propulsion module can be seen here for the direct drive engine, and we see that in the middle there's a boost converter which stabilizes the fuel cell voltage and has an efficiency according to the measurements of Mr. Wienhausen. On the right hand side we have a simple three-phase inverter, a V6C configuration, which feeds the low-speed electric motor and has losses based on the semicon handbook. The gear drive engine again looks much the same. We will only replace the V6C with an isometric half bridge, as we need some supply for the switch lattice machine. And the losses of this converter are calculated based on the maximum current control scheme. And the inductors here are actually the phase inductors of the switch lattice machine. Regarding the power source, we will apply fuel cell, since batteries are too heavy. And our model can calculate the heat generation and takes into account load dependency of the heat generation and the dependency on whether water or steam is generated by the fuel cell. Further, we can calculate the consumption of hydrogen and air, and also the composition of the exhaust gas. And we will be able to emulate the electrical behavior, as shown in the picture below. This is a voltage characteristic of the ECPO NM12 fuel cell, which is a baseline model here. And we can also have some information about the stationary short circuit current. The baseline model is the ECPO NM12 in terms of size, weight, and efficiency, and this is a fuel cell from automotive application. Further, we will need a turbocharger to stabilize the temperature and pressure of the fuel cell over all altitude level. Further, we can recuperate some energy from the exhaust gas and thereby enhance the efficiency of the electrical engine. To determine the weight of the turbocharger, we will calculate the pressure ratio, considering inlet losses and also the dynamic pressure at cruise and top of climb, but we will not apply the propeller as first stage of compression, as in the electrical engine concept. The propeller is not necessarily aligned with the turbocharger, as we are anyway connected by piping to the fuel cell. We will calculate the power demand, assuming an isentropic operation, and the power is regenerated or supplied by an electrical drivetrain. The baseline model is an MAN TCR series ship engine turbocharger in terms of size, weight, and mechanical efficiency. Regarding the protection system, we actually only need a breaker here to clear any faults. Further, we will apply varistors and discharge resistors to have an automatic overvoltage protection and an automatic DC link capacitor discharge. Further, we will connect the midpoint of the drive system to the aircraft body. By this, we will reduce the isolation requirements and we will separate the ground connection from the power flow. We have also an inherent fault clearance support here, since at fault instance, the turbocharger will phase out, thereby inhibiting the air supply of the fuel cell. So the fuel cell is not able to sustain the fault current and slowly decreases the fault current, which supports the breaker by shutting it off. The baseline model regarding the breaker are child power contactors from railway application in terms of size and weight. The cooling system has, in principle, two main heat rejection paths. The first is, as usual, the dissipation towards ambient. The other path is heat rejection towards the fuel flow. The liquid hydrogen needs considerable heating before being ejected to the fuel cell, and this is done by a fuel preheater. The actual output temperature of the fuel preheater is dependent on the pressure rating and operation temperature of the fuel cell, as we need to achieve that temperature after the compressor. The cooling system itself splits into three cooling circuits. First is the cryogenic cooling circuit, which operates on -250 degrees C and up to -233 degrees C, and is only applied to the direct drive engine, as this engine type is the only engine which applies superconductive components. The cold circuit exclusively rejects heats towards the fuel flow, so the heat rejection capacity is quite limited, and it's operating on a temperature of 22 degrees C, whereas the main heat dissipation path is over the hot cooling circuit, which operates 20 degrees C below the fuel cell temperature. The baseline models in terms of size and weight are for the cryocoolers and fluid pumps adopted from the findings of Mr. Rodney. And regarding the heat exchangers, we will apply the AKG line H, Funke GPL or GPLK series, which are heat exchangers from industrial applications and serve as a reference for size and weight. With this, we can go on with the electrical engine construction. And actually, the size of the direct drive engine and also of the gear drive engine can be achieved by stacking the engine modules on top of each other. So we can focus on the engine module size. We can see here that this is actually a cylinder, and the dashed line refers to the superconductive module. The rest of the cylinder is occupied by the remaining propulsion modules, so by power electronics, breakers, and the fuel cell. And the solid line surrounding that is the actual engine diameter. The gear drive engine construction is a bit complicated. We have here each propulsion module put in an own cylinder, whereas each cylinder contains the switch electric machine, power electronics, breakers, and the fuel cell. The diameter of the cylinders is the same as the diameter of the switch electric machine. And this propulsion modules are placed behind the gearbox. which combines the power offsets of the propulsion modules and gives it to the engine spool right in the middle of the engine. For the size determination, we will exclude the turbocharger and cooling system size, since these systems are in principle separable from the engine. And these systems have a considerable air intake and output, so we can use them to facilitate the boundary layer on the aircraft, maybe at the wing or at the fuselage. So the placement of the system is rather subject to overall aircraft design, in a sense not covered here. With this, we have information about efficiency, size, and operation. So the holistic model is there and ready for retrofit. We looked at the ATR72-600, the Airbus A320neo, and the Airbus A350-900, and equipped these aircraft with the electrical engine. Let's start with the RTR. And this is the aircraft, and that is the configuration we will apply for the electrical engines. With this, we will certainly alter the aerodynamic behavior, and this will also lead to some snowball effect on the aircraft. But we will assume a constant aircraft in this thesis, so we will neglect aerodynamic and effects and snowball effects. Hence, this will enable us to directly compare it to the conventional turboprop engine and to apply the power demand of the conventional aircraft, which has been provided by the Institute for Aerospace Systems. Our reference engine is a Pratt & Whitney PW127M turboprop, which can provide a propulsion power of up to 2 megawatts. It's a reference for size and weight for our electrical engines, and we refer in this case to the bare engine dry weight, as it is given in the certification datasheet. The electrical engines will provide a power of 1 megawatt each, and we will examine 3 different variants. The direct drive engine, the gear drive engine with 250 kilowatt SRMs, and the gear drive engine with 500 kilowatt SRMs. In this context, we will consider the operation points cold weather, hot weather condition takeoff, and elevated airfield takeoff, and the operation point top of climb and cruise. So that's the baseline scenario. We can very plainly see that we are far too heavy, but what is the reason? First of all, excessive cooling weight. We suffer here from a very low temperature differences of 2.5 degrees C towards ambient during hot weather takeoff, which leads to this excessive design as the heat exchangers will need very large surfaces. But in addition, we have already an excessive weight in the drivetrain itself. This is due to the fact that the fuel cell is already as heavy as the turboprop engine. Further, the turbocharger is already as heavy as the reference engine, although we have a far lower rating, and we are, since we are providing 4.5 bar and have a ratio of 6.3 to 1. So this is mainly a shortcoming of the baseline model, which is from a ship engine turbocharger, which is hardly optimized for weight. Regarding the size, we can see here that the direct drive engine is quite okay regarding the diameter to length ratio, but the gear drive engines are to some extent a bit excessive, especially the 500 kilowatt type gear drive engine, which is not anymore considered in this thesis. So we will focus on the 250 kilowatt SRM based gear drive engine, and we should remark that this size estimation excludes turbocharger and coolings. And we should also have in mind that the actual size assessment needs the effect on the aerodynamic effects of the aircraft. And further, we will be able to reconfigure the gear drive engine. For example, we could switch from one engine module with 4 propulsion modules to 1 propulsion module per engine module, and therefore stacking 4 engine modules in a line. By this, we can reduce the diameter to 500 millimeters, and this in turn will lead to a longer engine, and in the consequence to a diameter to length ratio of about 0.18, which is in the same range as the turboprop engine. But this is actually future work. What can we do? First of all, we need to analyze that the heating system has a very sharp load peak at hot weather takeoff. During cold weather takeoff, the loading is quite negligible. At hot weather takeoff, it is very remarkable, and at elevated air takeoff, it's moderate. During top of climbing cruise, it's almost nothing. So what can we do about this excessive thermal load? We could adopt the operation scheme of the fuel cell. We will adapt the operation temperature during hot and elevated airfield takeoff to a temperature of 180 degrees C to facilitate heat dissipation. And during cold weather takeoff, we will set the operation temperature to 76 degrees C to facilitate the fuel cell operation itself. And at top of climb and cruise, we will head for an operation temperature of 180 degrees C to avoid the necessity of a charged air cooler, as we have here the highest pressure ratio between ambient and the fuel cell system. This will be combined with the efficiencies of prospective conventional engines. Literature expects that conventional engines will be able to achieve 60% cruise efficiency up to 70% cruise efficiency in future. Therefore, we will design the electrical engines accordingly. So the design points are 60% cruise efficiency, 65% cruise efficiency, and 70% cruise efficiency. All this put together leads to a much more favorable heat distribution. We can see here that during takeoff, the thermal load on the cooling circuit is almost the same for all conditions. And we increase the utilization of the cooling system during top of climb and cruise. Further, we can reduce the peak of the thermal load during hot weather takeoff by a factor of 55. But we need further considerations for weight adaptations. Let's have a look at the drivetrain of the direct drive engine, which is the bar on the most right-hand side. And we can see here that the electrical drivetrain without the fuel cell is already 1/3 of the reference turboprop engine. Further, we can see here that the fuel cell is already as heavy as a turbocharger, but literature expects that the fuel cell weight will improve in future by a factor of 3. So we have another third of our reference engine. Further, we can expect that we can significantly improve the weight of the cooling and turbocharger systems, as we saw that the cooling system design for the baseline engines is rather poor, and the turbocharger has some shortcomings from the baseline model. So this put together results in a pursued weight distribution of 1/3 for the electrical drive, 1/3 of the weight for the fuel cell, and the remaining third for mechanics and cooling. With this, we can determine the improvement factors to achieve a direct drive engine with a similar weight as a turboprop engine. With respect to the baseline engines, we have some improvement factors. So we can see here that the electrical drivetrain can actually stay the same. We need to improve the fuel cell, as already mentioned, and the turbocharger by a factor of 20. This may sound huge, but we should keep in mind that we operate just at 180 degrees C at maximum. So we can replace the steel with plastics or aluminum, and this with regard to the density of this material is already a factor of 4. Then we can apply here a single stage turbocharger with a pressure ratio of 6.33 to 1. In the baseline model, this is a 2-stage turbocharger. So this is another factor of 2. And by further customization, we should be able to apply some lightweight design measures and to reduce the 2 parallel turbocharger systems we would require for the ship engine baseline model to just 1 bigger turbocharger, which would be another factor of 2.5, and this in total is a factor of 20. The cooling system needs to reduce by a factor of 55. Again, this sounds remarkable, but it's actually the thermal load reduction which we saw previously. Regarding the gear drive engine, the weight improvement factors differ a bit. We can see that the electrical drivetrain more or less stays the same. The fuel cell needs to increase a bit further in power density, and the turbocharger needs to reduce the weight by the same factor. Further, the cooling system needs another factor of 2, but this should be achievable by customizing the heat exchangers from the industrial application. On aircraft level, this will result in best case into a weight reduction of 250 kilograms, or in worst case, in a weight increment of 300 kilograms. Or measured in passengers, for the best case, we can take 2.7 passengers more on the aircraft. In the worst case, 3.2 passengers have to step out. With this model, we can also compare the direct drive engines with the gear drive engines. To recall, we are assuming here a 99.9% efficiency of this fully superconductive machine, which has a power density of 50 kilowatt per kilogram. And we will apply a comparative study to put the direct drive engine versus the gear drive engine. We will apply the weight improvement factors of the gear drive engine, balancing the Pratt & Whitney 127N turboprop engine, and we will neglect the parasitic heat input into the cryogenic cooling system, and we will also apply a power to autohydrogen conversion catalyst, which supports the cryogenic cooling circuit. We will determine with this measure what we will require as a minimum efficiency to get a direct drive engine of an equal weight as a gear drive engine, and the minimum power density required to get a gear drive engine with the same weight as the direct drive engine. The result can be seen here. The dashed line is a reference gear drive engine. The lower stars refer to direct drive engines operating on a superconductive machine temperature of minus 233 degrees C. The upper stars are related to direct drive engines operating on minus 250 degrees C. We can see that for the lower operation temperature and the power density of 50 kilowatt per kilogram, we will need at least an efficiency of the superconductive machine of 99.4% to have the direct drive engine lighter than the gear drive engine. With increasing operation temperature, we can reduce this minimum efficiency to 98.5% if we do not apply a conversion catalyst. And if we do, we can reduce the minimum efficiency to 98% with a power density of 50 kilowatt per kilogram. So to get a gear drive engine and direct drive engine lighter than a gear drive engine, we will require a superconductive machine operating on minus 233 degrees C and a power density of 50 kilowatt per kilogram with at least 98% efficiency. Regarding the power density, we will require at least 16.5 kilowatt per kilogram at a superconductive machine efficiency of 99.9%. With this, we get an equal weight of the direct drive engine as with the gear drive engine. For decreasing efficiency ratings, the power density figure will rise. So to conclude this, it's rather uncertain whether a direct drive engine can actually achieve a significantly lower weight than a gear drive engine. Let's have a look what we found out for the Airbus A320neo. This is the configuration we applied. So we replaced one LEAP A1 turbofan engine with 4 electrical engines, which with each engine providing about 6 megawatt of propulsion power. We again assume a constant aircraft. And on aircraft level, we will, in best case, reduce the weight by 1.9 ton. And in worst case, we will add 2.1 tons to the aircraft. In passengers, this will be additional 20 passengers or 22 passengers stepping out. Regarding the improvement factors, we will have improvement factors in the range between 1.5 and 4 with regard to the presented ATR 72600 engines. And the main improvement factors apply for the cooling system, the engine spool, and power electronics. Regarding the size, we can see again that the direct drive engine should be rather acceptable, whereas the gear drive engine needs some reconfiguration as we have a quite big diameter. Regarding the Airbus A350-900, we replace a Trent XWB-84 turbofan engine with 6 electrical engines, and each of these engines will provide 12 megawatt propulsion power. We again assume a constant aircraft, and we will reduce the aircraft's weight in best case by 4.5 tons, and in worst case, we will increase the weight by 6.4 tons. So in one case, 48 passengers will step in additionally, and the worst case, 67 passengers will have to step out. Regarding the improvement factors, again, with regard to the ATR 72 electrical engines, we can see that the improvement factors will range from 1.5 to 8, whereas 8 applies for the spool. And another big figure is for power electronics and the cooling system. We actually put 2 engines of the Airbus A320neo in a row. So that's why the engine spool needs to halve with respect to the Airbus and A320. Regarding the size, as said, we put 2 A320 engines in a row. So the diameter stays the same. Again, for the direct drive engine, could be acceptable. For the gear drive engine, should be reconfigured. Yeah, with this, I would like to conclude my talk. We saw that aviation faces a demanding decarbonization goals, and that recent electric propulsion schemes apply centralized power sources. We propose instead to decentralize the electrical propulsion also for its power sources. And we propose the electrical engine concept, which is a separate autonomous entity in a modular structure. We presented the direct drive engine and the gear drive engine. And we developed an holistic electrical engine model to enable the concept assessment. We considered external constraints. We take into account liquid hydrogen characteristics, and we developed models for the electrical engine components. In this regard, we laid an emphasis on high-speed switch lattice machines and developed a novel rapid SRM design tool and found new high-speed power-dense switch lattice machine designs. We proposed a high-altitude compatible power electronics design and grounding and protection scheme, which is compliant with the CS25 certification specification. We applied these engines to some aircraft in a retrofit approach to determine the electrical engine component requirements. For this, we applied efficiency ratings for prospective conventional engines, and we injected aerodynamic effects, and we found that the electrical engines need some reduction in size and weight. Whereas the improvements for the ATR 72-600 are rather moderate, but for the larger aircraft, A320neo and A350-900, it's quite extensive. Further, we saw that only little adaptations are necessary if appropriate weight is provided for the electrical engines, as we applied the same propulsion modules for all aircraft. For the gear drive engine, we only had to adapt the gearbox and the engine spool. For the direct drive engine, the adaptations limited a limit to the electrical machines. We also saw that direct drive engines are only superior to gear drive engines for optimistic assumptions regarding the fully superconductive electrical machine, since cryocooling system components quickly offset any benefits of superconductors. Regarding future work, we showed definitely examine the aerodynamic effects to get some more precise power density and size requirements for the electrical engines. And on engine level, we should clarify the necessity of a boost converter and also of the breaker, as we could, for example, protect the propulsion module by shutting off the reactant supply. Further, we should review the redundancy requirement on engine level so that we could obtain a lighter engine spool design. And we should customize the propulsor for higher gearbox output speeds, as we in this thesis apply the output speeds of conventional turbofans and propellers. On component level, we should verificate our models by more detailed approaches and by demonstrators, and we should advance the cooling system. We, for example, could consider heat pumps, and we should take into account the transient thermal behavior as we design the electrical engines for constant maximum power of, for example, 1 megawatt, whereas the turboprop engine has the maximum power of 2 megawatt for a certain range of time. Last but not least, we should also reduce the DC link voltage so that we can apply gallium nitride converters. With this, I would like to close my talk. And thank you for your kind attention, and I'm open for your questions.